Welcome to Summarize Science. In 2022, astronomers witnessed the brightest cosmic explosion ever recorded, a gamma-ray burst nicknamed the BOAT for Brightest of All Time. This event, officially GRB 221009A, was so powerful it sent ripples through our understanding of the universe. But it also created a huge puzzle. Despite its incredible brightness in gamma rays, our most powerful neutrino telescopes saw absolutely nothing. This burst was detected by numerous instruments in space and on the ground, giving scientists an unprecedented look at a GRB's afterglow. The energy of the light, or photons, detected was off the charts, reaching into the multi-TeV range, which is trillions of times more energetic than visible light. These observations challenged the standard models that have been used to explain GRB afterglows for decades. To solve this, the researchers in this paper proposed a different kind of explosion. Instead of a simple, uniform, top-hat jet of energy, they modeled it as a Gaussian structured jet. Think of it like a flashlight beam that's intensely bright at the center and gradually fades out towards the edges. This structure can explain the extreme brightness we saw from our viewing angle without requiring an impossibly large amount of total energy for the explosion. The researchers tested their model by seeing if it could reproduce the actual data collected by telescopes. As you can see in these graphs, their model, shown by the solid curves, provides an excellent fit to the observed data points from the Agile and Liceso observatories. This confirms that the structured jet is a very plausible explanation for the weirdly bright and long-lived afterglow of the BOAT. With a working model for the gamma rays, they could now tackle the neutrino mystery. GRBs are thought to be cosmic particle accelerators, capable of creating the highest energy particles in the universe. If they accelerate protons to extreme speeds, these protons should interact with the light of the afterglow to create particles called pions. These pions then decay, producing a flood of high-energy neutrinos, often called ghost particles. Using their successful model, the scientists calculated the expected neutrino flux from GRB 221009A. Here, the colored bands show the predicted neutrino flux based on the model's parameters. The dotted lines show the sensitivity limits of our best current and future neutrino detectors, IceCube Gen 2 and Grand 200K. Crucially, the predicted flux lies just below these sensitivity lines, which perfectly explains why no neutrinos were detected. So, what would it take to actually see neutrinos from a GRB? The researchers explored this by simulating different scenarios, changing key parameters like the explosion's energy and the density of the surrounding gas. These plots show that to get a detectable number of events, you need a perfect storm of conditions. You need an extremely energetic, relatively nearby burst that is very efficient at accelerating protons. So let's recap the important findings. The brightest gamma-ray burst ever seen can be explained by a jet that's structured, with a powerful core and weaker edges. This model successfully predicts that the neutrino signal from this event, while present, was too faint for our current observatories to detect. This tells us that while GRBs are still prime candidates for producing cosmic rays and neutrinos, only the most energetic, nearby, and perfectly aligned events will give us the multi-messenger signals we're hoping to find in the future.